So in the last video, you guys saw that the width of the secondary maxima or the secondary minima is the same, correct? Now what we are trying to figure out is what is the width of the central maximum. So for that, see, for the central maximum, it's between two first secondary minima, correct? So basically the distance is twice that of everything else, or we can say beta naught. Beta naught is the width of the central maximum. So beta naught will be 2 times of beta, where beta is the distance from center to the first secondary minimum. Okay, so if you look at the figure, see, if you look at the figure, we have from center, so we have lambda by a, correct? So in total, the width of the central maximum will be 2 times of beta, correct? So beta naught is 2 times of beta. This is what we were discussing. So we have beta naught is equal to 2 times of d lambda divided by a. Okay, so this is what we get as the width of the central maximum. Now, so far whatever we have seen, important points what has to be noticed here. See, one thing is beta naught, the value of the central maximum, it directly depends on the wavelength, correct? So more the wavelength we use, bigger will be the central maximum, and it is inversely proportional to the slit width, correct? So if you choose a slit width to be very big, then the central maximum will keep on reducing, or if the slit width is very narrow, then central maximum is very high, correct? But one important point is the intensity of the central maximum is independent of the slit width. Okay, we are talking about the intensity of the central maximum. Okay, so this is one thing, and the second thing is, as we keep on going away from the central maximum, what happens? The secondary minimum and the secondary maximum, they're of the same width, we proved it, but the intensity of these fringes will keep on reducing as you go away from the central maximum. Okay, so these are certain experimental observations what we can figure out by the diffraction pattern. Okay.